So the part you had missed is going to come back on next Tuesday, which would be our last lecture day. But the part you had missed has to do with the physics of these cantilevers. One part of it is to do with the physics of these cantilevers. These are extremely tiny micron scale structures with nanometer scale thickness. And they make incredibly efficient nonlinear localized modes, what are called intrinsic localized modes also. And this is a review paper that the main person here who did the experiments were Al Sievers, and that's him. And Al Sievers actually is world famous for all this work, which is both, in the funny domain of both applied physics and engineering and of nonlinear physics and applied mathematics. It's kind of in there. It encompasses everything. And it's a long paper. It's a long authoritative paper, which is very, very well known and well worth exploring if you're interested in nonlinear phenomena. So anyway, so we discussed that, and then we discussed these nonlinear localized modes. As you see here in Al Sievers' experiments, these are all dark areas or where energy gets localized. This is basically the same cantilever as that. So the cantilevers are excited by driving them, and they're driven from this point in time, where the timer is set at 0 to about 18 milliseconds or so. And then after that, once they have trapped enough energy, they're let go, the driver is turned off, and you see that energy gets localized instead of moving around. And the physics of these localized energies is tied to the fact that these are cantilever structures. And these cantilever structures kind of roughly have the following feature, that the potential associated with this system's Hamiltonian will have a spring part roughly. And the spring part is how these cantilevers are connected by this bus bar. And the quartic part is an on-site nonlinearity that comes with the structure of the cantilevers. So you have an on-site nonlinearity and you have a harmonic coupling. And this combination is particularly well suited for giving you these nonlinear localized modes that many people also call breathers. Breathers because they sit and just, the energy goes up and down, up and down, up and down. They're extremely stable, but eventually they do break down in most cases. And here you can see some amount of that breakdown. All the experiments are more, complex because in a real experiment you have dissipation effects and so on. So the exact same physics that you're going to get by making the system, on a computer and integrating it in time where energy is conserved, and the physics you get in a system like Al Sievers' system are not exactly the same unless great care is taken. And this, of course, is why these experiments are so incredibly difficult. They look simple, but once you get into them and once you start to set them up, you begin to see that for every assumption that a theoretician makes, it's an experimentalist's living nightmare, because the experimentalist has to now rig up, right, the experiment just right, such that the precise theoretical conditions can be mimicked. So, and they do it, which is amazing. I had asked a friend of mine who is one of these great experimentalists in Chile. Actually, I showed you his work. No, I haven't showed you his work. I will show you his work. I was asking him that can you take an elastic sphere, for example, a stainless steel sphere, and compress it by up to 10-15% of its radius? He said, yes, no problem. Um, without with all the assumptions you have, I can do it. I wanted to hear that. Second, I wanted to hear, hey, Francisco, can you make the system frictionless? He smiled for a while and he said, well, I'm not that good of an experimentalist, but I can come pretty close. And I asked him how. He said, well, the way you get rid of a lot of these frictional effects in the granular systems is you coat them in liquid glass and let the glass solidify. So if these granular particles, stainless steel particles, or whatever particles you have, they are glass coated by a sort of almost nanoscale layer of glass, and they hit each other gently, the frictional effects go down dramatically. I said, I can't make it zero, but it'll be near zero if I can pull it off. So, this is the kind of wisdom. I've never read it in any journal, but he had tried this and come very close. So a lot of this stuff we don't learn in class, but it's real physics. It's very complex physics that goes into the experimentalist's work. And Alcibus's experiments are also pieces of art, just like that. They're very well done. Anyway, I talked with Tony a little bit on Tuesday about how our system was made, where we took a Fermi-Pascal-Ulam-Singo system. So it's not the same system as this one, where you have an on-site term only, where localized modes are much easier to form. But we had another term like this, which was quartic, which is our Fermi-Pascal-Ulam-Singo beta model. And then we squeezed a bond here at t equal to 0 and let it go. And by squeezing the bond here and letting it go, we managed to make something similar to what Sivas had, which is a nonlinear localized mode, as we call them, or localized nonlinear excitation, as we call them. And then this thing decays by emitting solitary waves. And we discussed how this works. And that's in the video that you need to see. And then we came back to the fact that the Fermi-Pascal-Ulam-Singo system in the alpha model, how it is to be mapped to a Korteweg-de-Vries equation. So that was discussed also. The alpha model, not the beta model, not the ones that we are talking about now, but the alpha model can be mapped to a Korteweg-de-Vries equation. And that's this equation here, or this equation here, means the same thing. So we discussed that. We discussed a little bit about how it's solved and how real experiments can be done, and one can also have fun, as you can see. This is in a channel in Edinburgh. In fact, the author is from there. I think the author of this paper is a gentleman by the name of Chris Eilbeck, and he's from Edinburgh. So you can see here that you have a long channel, which is not very deep, which are the conditions that make it comparable to a Korteweg-de-Vries problem. And you can see a very nice soliton, and you can see this more perturbed water here. And the soliton is headed from the bottom here to the top there. That's what's happening. And so that's the one soliton solution for the Korteweg-de-Vries problem. But these nonlinear equations, they don't have unique solutions. Uniqueness doesn't apply. So there are also these multi-soliton solutions of the same equation. This is a system where the very same kind of conditions apply. It's a long channel. One of the English rivers, Severn River, they say. And here you see somebody surfing over what is clearly a multi-soliton wave. This is the first one. This surfer is ahead of it. Second one, third one, fourth one, fifth one, and there are more. We have done some explorations of this system just for fun, never published it because people have worked on them. There are big papers on them. So we have just discussed the Korteweg-de Vries problems, one soliton solution. But be aware that there's a 2 soliton, 3 soliton, and the n soliton solution also. And all of these are available in the literature. Quite amazing that so much can be gotten out of these systems. So this is kind of where we finished. And now I'll move on. I'll not move on, but I'll add a layer. I think that's a better way of saying that. I'll add a layer. And this layer is the granular problem, the Hertz problem. Just like the Fermi-Pasta-Ulam-Singo problem, which cannot be solved analytically in the discrete lattice form, the Hertz problem also cannot be solved analytically in the discrete lattice form. Both of these problems, the fact that they cannot be solved analytically, suggests that they are non-integrable problems. And the physics of non-integrable problems are dramatically different from the physics of integrable problems. And among the integrable problems, if you recall, I mentioned the Korteweg-de Vries equation being one of the integrable problems. I mentioned something called the nonlinear Schrödinger equation being one of the integrable problems. And I also mentioned the Sine-Gordon equation as one of the integrable problems. Just to remind you, let me take you back where we did this. I can't tell you how good it is to have all these slides together because at first I thought what I'm doing is insane, but now I realize it wasn't so insane because it was a good idea actually. I can show you stuff by simply scrolling back sufficiently far. When did we do this? Not that far back in time, actually. Yes. This was the slide where we discussed the solvable systems. We talked about the Sine-Gordon problem, which is same as the wave equation, but with the sinusoidal term. We talked about the Korteweg-de Vries problem, which is the one that we have talked about several times. And the one that we haven't talked about, which I hope to talk about before I finish on Tuesday, is a nonlinear Schrödinger equation, or the cubic Schrödinger equation. This nonlinear Schrödinger equation is tied to a Hamiltonian which is complex, as opposed to real Hamiltonians. This one typically uses the Poisson bracket to set up the equations of motion if you start from that Hamiltonian. So it's a classical equation. If you use commutator brackets, you get the Schrödinger equation. Okay, and the nonlinear quantum Schrödinger equation. And the reason why I'm mentioning this is because if you could take a continuum problem of this problem, and instead of making it just take this problem. If I make a continuum model of this problem, LC versus problem, I'm going to end up with a nonlinear Schrödinger equation. So I'm giving you this big connection as to why the nonlinear Schrödinger equation is also connected to what we are talking about, because a problem like this smoothly maps over in the continuum limit, the nonlinear Schrodinger equation. This particular problem and the nonlinear Schrodinger equation problem, they are particularly well suited for studying these localized excitations called breathers. Mathematicians call them breathers. So for studying breather physics, it's very well suited, that particular nonlinear Schrodinger equation. And when people study nonlinear fluctuations in the Bose-Einstein condensate, which one can now make in the laboratory, the Bose-Einstein condensate, by the way, also supports these kind of breathers and solitons. So this equation, the nonlinear Schrodinger equation, is also a widely used equation, just like the Korteweg-de Vries equation. It's a little bit more complicated. It has more physics in it. It kind of ties in with more phenomena. So I did not prioritize that because it'll be much wiser to kind of link it with things you have learned so you can actually relate to it in some kind of a semi-intuitive way. That was my objective. Anyway, let's move back to the Hertz problem, which we want to study. So the Hertz problem, the main point I made, just like the Fermi-Pascal-Olamsingo problem, is also a non-integrable problem. It's a problem that brings its own complex physics, and we want to look at it. Unlike those problems, which began more than 60, 70 years ago, the Hertz problem began in 1983. So it's relatively recent. It's about 43 years ago that the Hertz problem was discovered, if you will. And like many problems, the Hertz problem was discovered without much planning. So a friend of mine, a very, very well-known physicist, mathematician, and engineer. He's a complete package. Okay, he's a complete package. This gentleman here, his name is Vitaly Nesterenko, a very distinguished scholar. Vitaly is fully a complete package. Vitaly, as I said, is a physicist, a mathematician, and an engineer. He's all three. He's good at all three, better than many people I know in all three of them. Not only that, he's also an experimentalist and a theorist. So if you ask for somebody who knows everything, he's an excellent candidate to be, looked at. And this is honest opinion. So anyway, Vitaly was a scientist at the Lavrentiev Institute in Siberia. And the Lavrentiev Institute is a kind of institute, part of the Russian Academy of Sciences, that did a lot of this applied science and engineering work. And he was a very senior person. For a long time, he was the director of the lab. And there was a time when the Russian government made an observation. And the observation is following, that the nuclear reactors that they have in Siberia, those nuclear reactor walls were not as good quality as they wanted them to be. So over time, the wear and tear was quite big, they thought, and the reactor walls would crack up over time. Obviously, this is unsafe. Radiation leak and all kind of things can happen. So they wanted the scientists to be able to make sure that these reactor walls can be better made. And one experiment that was run was, you have the walls, let's say like a cylinder, and the inner side of the cylinder, they put a layer of sand, thick layer of sand. And the idea was that the sand layer would damp the vibration. It's a very reasonable idea. And they did this thing, and they ran some experiments, and they found that the exact opposite thing happened. They found that the walls were cracking up even more. And this is when Vitaly was requested to solve this problem. Now, Vitali is basically, as I said, a physicist, a mathematician. Those were the things he did first, I think, and also an engineer. So he rigged up this experiment just to mimic the physics as he saw it. So he took this quartz tube, he put some stainless steel balls, and he put a pressure gauge, and this is a copper rod on the other end, just gently touching the last of the stainless steel balls. This is what he did. And then he took a striker on the right side and made an arrangement such that he could fire this striker, and the striker would go and hit this last grain. Now, this is a very cleverly designed experiment. And the reason why I emphasize that is because these vibrations that the walls were feeling were not very large vibrations. Point is that the walls were very prone to getting damaged when the sand layer was there. And because it is a cylindrical geometry, the alignment idea, the alignment of a bunch of steel balls idea came because Vitali thought of the thickness of the granular layer radially. So it's like a bunch of grains from, so this is the inner side, let's say, and this is the outer side. Inner side to outer side is like a bunch of grains, as if they're in an alignment. It was a simplified model. Now, why instead of taking sand, did he take steel? That is because the sand grains are basically elastic grains. They are sufficiently large that they can be thought of as elastic objects, characterized by Young's modulus, Poisson's ratio, and all that. And sand is essentially quartz. So you can have a quartz sphere. That would be a glass sphere, right? In an idealized lab, a quartz sphere is a glass sphere. So you can replace a sand grain, a glass bead. But physics-wise, it may be better to study a steel ball, because a steel ball is more robust, it won't crack so easily, and a steel ball will likely give better experimental signals. Plus, quartz is pretty heavy. Steel may not be quite as heavy. And if you want to put some sensors inside these balls, so suppose you take a ball and suppose you slice it, you make a little hole in the middle, and you stick your sensor there, and then you surgically put your ball back together, it is easier to manage it with stainless steel than with quartz. So for a variety of reasons, Vitalis chose this particular system. He also wanted to treat the problem in the elastic regime. You see, if you hit it with a gun, the bullet will come and hit this system at something like 1,000 meters per second, like a kilometer per second. So a typical speed of a bullet would be 1 to 2 kilometers per second, very fast. So if you hit this system with 1 to 2 kilometers per second speed, even with a small striker, the steel balls will deform because it is too high in terms of energy imported over time. The impulse would be too great. The steel ball's deformation would drive it away from the elastic to the inelastic regime. So Vitali figured I can hit it at 1 meter per second, 10 meter per second, maybe even 20 meter per second, and still remain in the elastic regime, then go to the nonlinear regime. That is the reason why he wanted it to be rigged up in such a way that a gentle perturbation could be done. And then this is the standard pressure gauge. There is nothing great going on. Experiments were done in this period, 83 to 85. And the first paper that he wrote up, that's in this Russian journal, and that actually it came out in 83 in the Russian version. And the English version came out in early 84. Back in those days, the way it used to work was that American Institute of Physics, they translated some of the major Russian journals into English. And this was actually done by a group of very, very dedicated people who were mostly ex-Russian physicists who had moved to the US, and they could relatively easily translate paper by paper from Russian to English. It was a lot of hard work, and therefore it took some time to do it correctly. And I think this effort continues even today because the Russian journals which are published in Russian also have English translations available, excepting it's probably easier to do today than it used to be at the time. So the reference for Vitaly's paper is this particular paper. And this paper came out in early 1984, if I recall right. And it's a thin paper. It's like 5 pages or so. Not that much stuff going on, just raw data reported. And the claim basically that you see a soliton. That's basically what he reported. So why did he see a soliton? What does one mean by that? What Vitaly saw is once you hit it with a striker, all you record is one pressure pulse in this pressure gauge. It's like one bump in the pressure gauge. Clean experiment you do by hitting a striker, at the end of the day, you see one bump in the pressure gauge. He was not expecting that. He was expecting oscillations to happen. And that expectation led him to think that you should see some kind of a bump followed by various kinds of vibration signals in the pressure gauge. There was no such thing. And that led him to the conclusion that the striker impact passes like one pulse, one shot, and hits the pressure gauge. So therefore, it must be a soliton. There's a very famous experiment then that was done by him, as it turned out. And I, at the time, was not aware of it. Where did, oh, he's there. Okay. Everything all right?
I just have to switch rooms real quick, if that's all right.
Oh, yeah. Let us pause for a bit then.
Yeah, by the way, I wanted to tell you something. So while I was gone, so I was, of course, in the marriage, it was in the wedding, but I was still looking through slides, and I am much more interested in working in Toda potential. So,
Toda,
yeah.
I think,
So,
but your market problem will get you a paper if you can do it right now.
so yeah. So I am trying to do that. So I'm trying to do Fourier transform and all. So by doing Fourier transform, that time series, I get mostly nothing, just noise.
You have to play with that.
Yeah, I realized that
Yeah.
we have to do much more analysis in Fourier analysis as well.
Yeah.
Yeah, of course, I'm going to do that as well. But one more thing that I want to try is that can I use the potential to generate a time series? So basically, in my second semester, only last year, so I was using a double well potential to generate a time series. And
when you say generate a time series, what are you generating? What are you plotting?
So basically, a ball is bouncing in a wall. Using that equation. No, forgot the name of the equation.
Langevin equation or something?
Langevin equation. Yes, Langevin equation using noise term.
You have a noise term there.
Yeah.
Toda is not the best potential for it because of the exponential term. So what do you want to see in the time series? That's the other question that one needs to look into.
I want to see if the time series can be multifractal or not.
What will that give us anyway? Multiple scaling laws. You can't get too many scaling laws out of these because it'll be so noisy especially if it's driven by something which is a random noise. You have to be careful, I think, because multifractal means there are various power laws, right?
Yeah, there are various power
But
laws.
various power laws will only happen if there is some kind of a system stabilization going towards relaxation.
Yes.
Multifractal in time will only happen from that. We have done some work on it. I'll share with you separately.
Oh,
Not in the multifractal angle, but in another angle, where
okay.
we looked into relaxation phenomena in the kind of system that I showed for the Sieverts system of cantilevers. But this was long before I knew about Sieverts system, back in 96, 97 timeframe. And I'll share with you some of those in a separate Zoom that you and I can do.
Okay.
That'll tell you a little bit about the physics that happens. So if you look for multifractal effects, what kind of physics you have to put in by hand, because there should be a clear relation between the physics that you actually put into the system and what you get out of it.
Yeah.
So you shouldn't try to get out something without having a lot of control on what you put in there. It's almost like cooking some nice dish. Random mixing of spices will not give you a good dish. But if you want a good dish, you have to organize the spices and put them in the right amount and right order, such that we can do it. You're okay, Tony?
Yeah, we're good.
Good. So
Sorry about that.
no problem. So anyway, so that's what Nesterenko did. He published it, and he pointed out this is a nice nonlinear problem, but it was funny because Nesterenko, given the incredibly erudite person he is, he figured, well, I mean, this looks like this looks like a Korteweg-de soliton, probably. Channel, this, that, small perturbation. So he tried to see if he could describe it with a Korteweg-de soliton. And that's what he put down in one of his two early papers. I just cited one paper. And the physics of these systems moved quite a bit experimentally, but in terms of theory, it didn't move that much between 83, 84, and 1994, 10 years. 10 years is a magical number. FPU also has 55 to 65, nothing happened. So in 94, what happened was that I read a paper, engineering paper, where I learned that if you take a sand bed and if you put some sound going into the sand bed vertically downward, then the sound speed actually goes up as it goes deeper and deeper. As it goes deeper and deeper, because of gravity, the pressure in the medium builds up. It's a denser compaction of the grains, and the sound speed goes up according to a power law. I was very intrigued because I thought, oh, if there is a power law, first of all, we should be able to get it from simulation also, not just theory. And if we could do simulation, then we can also learn where the power law becomes important, because surely you can't have a power law at shallow depths. So what is the physics at shallow depths? That is not explained by these papers I was looking at, but they talked about this sound speed increasing with depth. So one of my very, very good collaborators and friends, Bob Sienkiewicz, and I, we constructed a two-dimensional granular column, deep column, thousands of grains. And then we gave it a push on the top with gravitation loading and wanted to see how this push goes down. And if we recovered the power law, and yes, we did. We were very excited. But then very quickly we realized that at the shallow levels, obviously it wasn't a power law, but the signal traveled like a pulse, like a non-dispersive or weakly dispersive pulse. And I didn't know what that was. You see, I didn't have a solitron background. I had heard the name, but that was it. I was very lucky. If I knew even what you guys know now, I may not have been that surprised, and then we wouldn't have found what we found. So I figured that I want to understand why you have this pulse propagation. And so I set up a horizontal granular chain, one single granular chain, just a bunch of spheres lined up, just like Vitali's experiment on the computer. And we gave it a pulse, and we discovered that it supports what looked like a solitron or something. But then when we looked at it in detail, we found that not only is it not a solitron, it's an extremely sensitive solitary wave. Solitary wave. Meaning, when we collided two solitary waves, there was very coordinated scattering, which of course won't be there if they're solitons. They'll pass through each other. So this is around the time when somebody informed me, in fact, one of Vitali's colleagues who I used to know well, Professor Joe Goddard from University of California. Vitali had moved by this time from Novosibirsk to University of California at San Diego, and he was a professor of mechanical and aerospace engineering there. And Joe Goddard was a professor in the mechanics, applied mechanics department or something. So Goddard and Vitali were very good friends and colleagues, and Joe was somebody I knew very well. And he told me, "Hey, Surajit, why don't you take a look at Vitali's work?" And that's how I became aware of Vitali's work. And then, of course, I called him, and we became, very good friends over time. And so I've known him pretty much, more than 30 years. So when I got into this problem, I realized that Vitali's KdV solution idea in this paper was not right, because it could not be explained with KdV. I could not get KdV. What I got was very different. And it turned out that Vitali also realized sometime around then also that there was a problem with the KdV. So he did a much more sophisticated mathematical analysis of this system. And I'll show you what happened. But before that, let's go back to the physics of the grains, how these stainless steel spheres interact. So this story takes us to 1881, long time back. Heinrich Hertz. Heinrich Hertz, the same Hertz of electromagnetic waves. Heinrich Hertz. Heinrich Hertz was, at that time, a mere 21 years old. And this guy was a genius. He died at 37 or so, 36 or 37. And the amount of work he did, path-breaking work he did in that very short life is mind-blowing, even to somebody who has lived for 100 years. Hertz took two elastic spheres, two metal spheres, let's say, and he studied that if we squeezed one against the other, there will be a circular cross-section. Of course, if these are spheres, there'll be a circular cross-section of where they would overlap, they would meet. And the distance between the centers of these two grains, that is the distance between this point and that point, would now come closer. So here, suppose R1 were equal to R2, this would be the diameter. And now this length between the two centers would be less than the diameter. So if you took this diameter, subtracted this length, that is what was defined to be the small delta. And this delta has a name, and the name is the overlap parameter. Hertz showed that the force, the repulsive force that will happen when you squeeze one against the other, That force is some constant times delta to the power exactly 3/2. That was Hertz's discovery. And this is known as the Hertz law, published in this German paper in 1881. The constant A obviously has information about the elastic objects in question, the two spheres. So Y1 and Y2 are the Young's moduli of the spheres 1 and 2. And sigma 1 and sigma 2 are the Poisson ratio of 1 and 2. And then you have this factor. That's what A is. So if you change it to one glass and one stainless steel sphere, your Y1 and your sigma 1 would change, for example. Here is a bit of an animation of this. I think I have to probably put it in slide mode to do that. You can see the circular overlap. And now you can see the measurements. This boils down to be the overlap. It's relatively straightforward to do this problem. The integrals are a bit tricky. So 150 years after Hertz did his work in 1881. No, not 150 years, 130 years after Hertz. In 2011, my students and I went back to this problem, and instead of doing two spheres, we did two solids of symmetry. So it could be any shape as long as they were symmetric about an axis, and we could press one against the other. So this shape, in this case, this circle, even if it were an ellipse, we took all kinds of shapes, symmetric shapes. For example, we could make grains where the shape would be like a star, or the shape would be, like a diamond, or the shape would be some other funky form. And it was a lot of fun for us to show that that shape is tied to the force law in question. Meaning, if you have circular shape here, that would give you 3/2. If you have some other shape, it'll give you a different power. In fact, pointier the contacts, the higher the power. So we could basically design grains where the Hertz law was more general than Hertz's original version. So anyway, so it is possible to do that. Let me get out of this mode. But there is the physics behind this law is very interesting. And the physics behind this law is actually very nicely captured by this plot. So let's focus on this plot. You see the dashed line here, the dashed line is a parabola. So if it were V delta goes as delta square, that would give you the dashed line. Will you ever get that in a granular system? The answer is yes. How? Well, instead of taking two spheres, if I took two disks, like two coins, basically, and press one against the other, you see now the overlap area would be a rectangle. That rectangle overlap area will give me a delta square. It will give me harmonic forces. So a chain of disks will not give you a solitary wave. It will give you a sound wave. Not a sound wave, but it's like a harmonic oscillation. So you see, in the Hertz problem, if the force is 3/2, then the potential is 5/2. If the potential is 5/2, that's steeper than square. So in fact, The blue line, which is the 5/2, goes softer than harmonic and then steeper than harmonic. So now what happens? When the grains start to press each other, when the compression is very, very tiny, the potential is even softer than the harmonic potential. But the moment the compression builds up, the potential becomes stiffer than the harmonic potential. And if it becomes stiffer than the harmonic potential, that also means it becomes energetically very expensive to keep compressing these grains because strong repulsion is there. So therefore, the grain compression must cease and the two grains must slowly decompress. And that's exactly the physics that happens because of this kind of a Hertz potential. Furthermore, it also tells you that energy transport from grain 1 to grain 2, where grain 1 and grain 2 have Hertz law working between them, this energy transmission must be relatively short-timed. It can't be a long, drawn-out process because it becomes energetically prohibitively expensive because of this steepness of the potential. And that's the reason why energy transport from grain 1 to grain 2 develops this solitary wave structure. Because if I'm going to run to you and I have a very short contact time with you and I need to give you information, I'm going to throw my information just to you and you're going to do the same thing to the next guy. So if you think of it very simplistically, this is the reason intuitively why these systems must have solitary wave structures. The math is complicated. And this is the equation of motion of the system that we produce. Now, the left side here is very common. U sub I is a displacement from the center of any grain I. N is the force law. So N is equal to 5/2 if you have spheres. But in general, we made it N, and we also realized that N must be more than 2 for it to be non-trivial. Because if N is 2, it becomes harmonic. So N must be more than 2. Forget about the capital delta now. Ui minus 1 minus Ui is just the displacement of grain I minus 1 minus displacement of grain I. And then same thing on the other side here. So this is like an equation of motion. Everything is normal. You get exactly this equation for a harmonic oscillator chain. If you were to place n equal to 2, 2 minus 1 is 1, so it's easy to manage. And you get a harmonic oscillator equation. But now, of course, you have an n minus 1 here in general. And further, you can also make provisions for this term delta, where delta is nothing but a precompression between the grains. So suppose I went back to Vitaly's system here, and I have one end wall here, and instead of having an open end on the right side, suppose I put a wall here, a wall that can transmit a perturbation, but a wall nonetheless, such that they can't, go on the right side anymore. So if I make the distance between this wall and that wall equal to n times the diameter of each grain, where n is the number of balls, then there would be zero precompression. That means the walls are touching each other at the end of the grains. But if I press one of these walls against the other a little bit, so if I take this wall and take it a little bit to the left, what will happen? What will happen is every grain here will get slightly squeezed. And if you press it harder, it becomes squeezed even more. So that is your delta. Delta is called precompression. And precompression is this applied pressure that places the grains in more intimate contact than they were had there been no precompression. It's an important effect, which will have important physical consequences. So we will now not worry about that, but it is there. So I'm going to turn off, now that I've explained to you what this precompression is, I'm going to turn off precompression. Now, actually by turning off precompression, I'm making my life more difficult. In fact, non-perturbatively more difficult. Why? You see, if I have the delta there, then this length scale associated with the delta can be compared with the length scale associated with ui minus 1 minus ui, or ui minus ui plus 1. Delta is that much, this is this much. And if it so happens that delta is bigger than ui minus 1 minus ui or ui minus ui plus 1, you can immediately see that I can take delta out and I can do a Taylor expansion inside. And I can do it for both the terms, and I'll get some nonlinear equation. And that will be a little bit easier to manage, maybe. Alternately, I can have very small delta, and ui minus 1 minus ui may be larger than that small delta. And then what will happen is I would take ui minus 1 minus ui out and do a series inside, Taylor expanded series. But now in that other limit, again, I can get a nicer equation. But now if I turn delta off, I have literally shot myself in the foot. Literally, with a rifle too. Why? Because I have lost my handle to do a perturbation. Delta equal to 0 means there's no way I can do a perturbation. Which means you have a strongly nonlinear problem in which you cannot do perturbation, which is pretty much the only technique we know to do anything, which means I have no way of generating a solution that is systematic. Which also means that I have to only guess the right answer, and that is the end of the story. If I got the answer, I go home. If I do not get the answer, I am officially cooked. Nothing can be done about it. So this delta is a boon in a package, but if you turn delta off like we did, you have shot yourself with a rifle in your foot with no hope of recovery. Also, these are macroscopic grains. Macroscopic entities have microscopic vibrations in them, which means energy is lost to internal degrees of freedom. So therefore, they are lossy entities. Not very lossy usually, but somewhat lossy entities. So therefore, when the grains compress each other, we call it force of loading. When the grains decompress, we call it force of unloading. And the ratio of this unloading to loading is what we define as 1 minus omega, or W. And this W is the restitution coefficient, which is a measure of how much energy is being converted from into the microscopic degrees of freedom. So in a simulation, of course, we can make this W to 0 or turn it on. But in real experiment, W is there. But we have this handle, which is a convenience thing. So this is a picture of a Newton's pendulum, which is basically this problem, different boundaries. You've already looked at this Fermi-Pastel-Ulam-Singo problem. And this problem I haven't told you, but it's also a very interesting problem that we have been working on. A relatively new problem as well. which also has deep roots in other areas of physics, especially in field theory. And it's physically the problem of an electron chain, a chain of electrons that are somehow hooked to each other. It can be set up with strong magnets. Now, but it's a bit of a crazy problem. And I'll tell you more about it later. So let us now see what Nesterenko was doing to manage this equation of motion that we had. Okay. Nesterenko, of course, had this problem in mind. Okay, Nesterenko had this problem in mind. And this is basically what Nesterenko did. I'll put it in slide form so I don't miss out on anything. So the way Vitali looked at this problem is he said, let us say delta is much larger than that ui minus 1 or ui minus 1 minus ui. So if you go back here, delta is much larger than this piece is what he's saying. So in that limit, Vitali shows in his paper that you actually recover this equation. I don't know why it is so. This equation in the middle here, this one. And this is actually a KdV equation as we discussed. You know, del 3G, del C3, then del G, del C times G. This is a classic KdV equation. So Vitali's point was that when delta is sufficiently large, you should get a KdV limit. But if delta is small, then you have a strongly nonlinear problem, because then you can't do perturbation with delta out and try to pretend that your grain-grain precompression is not a big deal. If delta is small, your grain-grain precompression is the big deal. Okay, and in that limit, see what he ended up with. And this was our point in that paper where we didn't derive this, obviously, but we showed that Vitali's KdV problem was not something that we were seeing in our simulations. You know, this is what great scientists do, right? When Vitali found out that we were not seeing his KdV result, he quickly checked and agreed with me. He said, yeah, you are right. We don't get it. I was very scared. I thought, wait a minute, I'm an assistant professor starting my career. Here is this big famous fellow. And once again, I have this unfortunate situation of telling this person that we don't agree with his conclusions. What would he do to me? Well, luckily, he did nothing. We became friends. And as a result, the subject moved very well, because it was basically at the time the two of us that were pursuing this. So my students and I, and Vitali's students and him. So this was Nesterenko equation. This is what it became. And you can see it's a very, very complicated equation. And while this equation cannot be solved, this equation can be reduced to something which is far more manageable. I won't do that. And that Vitali managed to solve analytically, which gave him a result that was not too good, but not too bad. And I can say that confidently because we were not doing this business. We were actually doing simulations for no compression or with little compression. And for that reason, we could actually check all the results that were around and see if we were in agreement, because we knew our results were perfect, because we had no dissipation, we had energy conservation, and we were getting results that were energy conserved to God knows how many decimal points. And this is basically what we were getting. We took our chain, we put a pulse on the left on grain 1, And that pulse, just like Vitali did in the experiment, naturally became a solitary wave. And then we put in perfectly reflecting balls. And we were hoping the solitary wave would just bounce back and forth. It has nowhere to go. And we could not be more wrong. We were totally wrong. Every time the solitary wave hit a wall, it broke down and reformed and made the secondary solitary wave structures, which made this system almost go to something like an equilibrium state. We couldn't believe our eyes. And how could that be possible? But before I go there, let me show you something which is very interesting. Remember I said that 130 years after Hertz, we developed this idea where we could play with the shapes of the overlap areas between the grains. That idea allowed us to vary the power, 5/2 power, or 2.5, right? 5 over 2 is 2.5. The potential goes as delta to the power 5 over 2, which is this one here. We could vary it between delta to the power 4, which is like a Fermi-Pascal system, and 2.01, which is slightly more than harmonic. So what I mean by this, let me escape from here. A little easier to manage. So this 5/2 is being varied. And we are varying it between 4 and 2.01. If it were 2, it's harmonic, right? By the way, this problem is very different from any other problem because what happens when the grains lose contact? No interaction. So interaction only happens when they compress each other. So the moment contact breaks, interaction ceases. That's also a property of the system. So what we found was this solitary wave's width, if you define a width. Now, how do you define a width of something like this? You can say that this is a peak structure. So the peak height is, let's say, so much. Let's say in this case, 0.7. And so this is the peak height. And at this height, at half the point, half the distance, 0.35, this is the width. Okay, whatever that number is. It goes, let's say, from roundabout -3 to roundabout +3. So what would then happen? I would say that half width at half maximum. So this is the full maximum. Half maximum is here. Half width means from -3 to 0 or 0 to +3 roughly. So half width at half maximum is how you measure the sizes of these structures, because they may be infinite for all you know. Further, if this power becomes precisely 2, this wave, this solitary wave, will essentially become a flat straight line, which means the size of the solitary wave will become infinite, which means the solitary wave cannot be accommodated. It is not there when you have a harmonic system. However, how wide can a solitary wave be? It can be only 1 grain diameter wide at the smallest, right? Because your unit of the system is 1 grain diameter. So of the physical system, not of measurement system, but of the physical system. So the solitary wave at least would be 1 grain diameter wide. So when this n here goes to infinity, instead of 5 over 2, when n goes to infinity, it becomes a hard sphere. So when you do billiard ball problem, assuming them to be hard spheres, you are actually doing a nonlinear problem, but the hard sphere has made things so bad that your potential disappears. You don't need to consider it. You just use momentum conservation and energy conservation. You can still get the right physics, but basically it means the solitary wave is one grain width wide. That's it. It's very profound. You go from one grain width to infinite grain width, which is no solitary wave. So all that physics is here. But what is really exciting is all of this fancy simulations, and in this case, it was simulation-based theory, can be seen experimentally. And this is my friend I was talking about, Mello here, Francisco Mello, and his then postdoc, Stefan Job. Stefan is now a professor in Paris. So Francisco and Stefan actually rigged up this experiment in their lab in University of Santiago in Chile. And this is actually a solitary wave, but not as a function of space, but as it moves through time. So on the vertical axis, it is a force recorded in a sensor that is embedded inside a grain surgically. I'll show you how it's done. And that sensor records a propagating soliton or a solitary wave with exactly the features that we had seen in our simulations. This picture, I don't believe, was published early. It was published much later. But the one that was published is coming up. This was a major discovery at the time. That paper appeared in 2005. Now, just a few more little things. We discovered that the width of the solitary wave, or if you will, the half width at half maximum of the solitary wave, follows this law. So if you set n equal to 2, 2 minus 2 is 0, which gives you the width of the solitary wave equal to 1. Now, sorry, if you, I made a mistake. If you set n equal to infinity, infinity minus 2, and 1 over infinity minus 2 raised to any power would be 0. That's how you get the 1. But if you put n equal to 2, what happens? You have a singularity. You have no solitary wave. So all of these were published in this paper in 2013. But let me also tell you what happens when you load, because this is something that I was giving a preview to Tony on Tuesday. So you see, if there is no loading, and if I do a perturbation to this granular chain, I get the solitary wave. This wave is the same as Francisco's wave here, excepting this is in space, this is in time, and this is in space. Otherwise the same. What are these guys? I'll come to that. I'll come to that. Hold your thought on that. But now as I start to pre-compress my system ever so little, you see what happens. You see the solitary wave shrinks a little bit in the amount of energy it carries, followed by an oscillatory tail. And as I load more and more, the solitary wave and the oscillatory tail comes closer until the two merge up and it becomes like an acoustic wave. Tony, I pointed out about the Bessel function to you. That Katya's paper beautifully presented. This is like your Bessel function solution. So Bessel function solution is like a solution like this, and this is the experience of a grain, of the velocity of a grain. That's what That's what this is. This is a snapshot in time. So therefore, is the experience of velocity of many particles in terms of grain number. But the other way of doing this is single grain goes through this in time. So let's go quickly to something I've discussed already with you. I collide two of these waves. I take a long chain, I make two striker hits at the two ends, and now the solitary waves go towards each other. And I make it such that the waves meet. You see, the waves can meet in the simplest case in two different ways. One is they can meet between the grains. That's one simple case. One is they can meet at the center of one grain. It's the second case. And then there are an infinite number of cases where they can meet between the center of a grain and the edge of a grain. So I'll leave out those infinite number of cases. I'll also leave out edge collisions. We have studied and published on them. They are different, a little bit different. But let us look at the center of a grain collision, because that is quite nice in its own right. So in this case, you see the center of a grain collision, and the grain at which the center is involved, is grain number 250. And in grain number 250, if you look closely, this is the line for grain number 250 here. And you see it goes straight through. There is nothing happening in grain 250, which goes to show that grain 250 acts like an infinite mass. It doesn't move. It's like a hard wall. Which, by the way,
Just like
is exactly what we have here. Hard wall. So this wall collision is equivalent, to this collision. But look at this scale. Here, kinetic energy in our dimensionless unit is 0.5. Now let us go much finer in our measurement. This is 10 to the minus 4. We are 10,000 times more resolved than this case. And now you see that, yes, grain 250 is still not going anywhere. But grain 249 and 251 and all of them, they are actually becoming active. And the way they are becoming active is they are making these teeny, tiny waves, which are exactly the same solitary waves that we have. It's just that they're super tiny. They carry super little bit of energy. And that is the reason why these babies show up. That's why I said, hang in there, I'll tell you what these are. I was really, really surprised when we found this result. And so when we first submitted this paper, actually this paper has a wrong year. It should be 2000. I was 100% certain that we would get a flat out rejection. We tried it in physical review letters. That's what we got. Then I sent to PhysRev. And I was quite certain that this is so bizarre of a result that we would get rejected. Well, we almost got rejected. We got 2 referee reports. Both were skeptical, but they didn't laugh it off. And one said, how do you know you haven't made errors? All of these things you are showing us could be errors. Prove to us it's not errors. So we had to extend our study to prove to the referees that these were not errors. Everything we were putting down were far above where our numerical errors ran. Good referee, this person was convinced, and we were let go. And this became a very famous paper, actually, down the road. Now, so this paper obviously intrigued Francisco. I didn't know that. I was visiting Francisco same year in Chile, and I had mentioned this work to him. Paper came out after I returned, but Francisco was very intrigued by the result. So he rigged up, brilliant experimentalist, he rigged up this experiment, which is one of my most highly cited papers. I was a co-author in that with one of my undergrads who worked in the Chile lab on this problem also. So these are the grains, and this is the observatory, which is a grain which has been surgically opened up, and one sensor has been embedded. It's an accelerometer, and it has been filled with resin in such a way that the mass of this grain is exactly the same as the mass of all the other grains. So its system remains monodisperse. There is a sensor here at the back end and a sensor here. So there's some echo coming. Is there a phone on? Any of you have a phone on? Tony, do you have a phone on?
Do you have a phone on?
Yeah. Vivek, do you have a phone that is on also? No? My phone is off, but strange. Sometimes a phone would do that. Anyway, so let me remove my phone from here. A little bit far away. So what I'm going to show you, actually it is best, this is the back end. Let us look at this picture here, this picture. This picture is being traced out by this guy. And here what you see, you see there's a time scale here. Early time is here, late time is here. So early time, this is one solitary wave that is moving from left to right, left to right. That's this one. After a while, there is a slightly reduced solitary wave that is moving from right to left, moving back that way. That is this fellow here. And then there is its first baby, and that is this fellow here. And this particular trace is a trace at the back sensor here, which is in dashed line. So this is the simulated version. This is an estimated, I forget what equation 5 is, but I believe this is the back sensor. Anyway, the story here is as follows, that in this experiment that they did, the secondary wave is almost a third or fourth of the size of this wave. Whereas in our simulations, this is 1 over 10,000. And the reason is very simple. The reason goes back to this acting as an infinitely hard wall, because this is the center of this grain. This grain doesn't really suffer any motion. So it's an infinitely hard wall. However, in Francisco's problem, this is a soft wall. A sensor is a soft wall. What happens when you collide against a soft wall? Your collision slows down. because you go to compress this wall and then slowly decompress it back. What happens if you have a hard wall? You have a very dramatic turn of the motion. In a hard collision, the amount of energy you lose is very little. But in a soft collision, the amount of energy that you can lose can be quite a bit. That is the reason why it happens. It loses quite a bit of energy to the second wave, which is our secondary solitary wave as predicted. So Francisco showed that if you actually could do this study with soft walls, which we have never done, we have done sort of it. It's hard to do. Your secondary waves would be much larger, but they're there, they're real. The effect is real. Now, what happens if you have these secondary waves? Well, what happens is, if the solitary waves continue to break every time they hit a wall, then all the energy in the wave would disappear, right? After a large number of collisions, you are only losing energy every time you hit a wall. So your energy must be gone. That is not physically possible, is it? Because there is no dissipation in this problem. So physically, it is impossible that you only lose energy, which means you have to have scenarios where you can also gain energy. And that energy gaining also happens in different kinds of collisions that happen between the solitary waves. When two waves are moving in the same direction and a big wave overtakes a less energetic wave, guess what the big wave does? It steals the energy of the less energetic wave. The big wave grows in these overtaking collisions. Similarly, when a small wave and a big wave hit each other head on, then the small wave grows as a result of the collisions. So you have this balance of these loss processes and gain processes. And it is this balance that over time drives the system to this very noisy equilibrium-like phase. Let me explain what I'm showing here. You see, suppose you have a granular chain and you are looking at the fastest moving particle in the granular chain. Moving to the left or right doesn't matter, so you just look at the fastest moving particle and just square the number. So that way left or right doesn't matter. It's kinetic energy. So if you look at the fastest moving particle over a long time and plot it out, you get this blue kind of plot. And here, you see that the large velocities here slowly die down, and eventually you hit a range where the velocities go up and down and up and down and up and down, up and down. It's not really equilibrium, but it's in a very wild equilibrium type phase. Fluctuations in energy are very large. And we had first seen this phase in the context of the Fermi-Pastel problem. And we called it a quasi-equilibrium phase. Looks like equilibrium, but it's not equilibrium. Very large energy fluctuations. So we get to this quasi-equilibrium phase as if it's an equilibrium, but it's not real equilibrium. Very large energy fluctuations. So I'm going to stop here now. By the way, this is actually an ergodic system. So if I took time average of one variable and space average of one variable, same variable, they will be, to the extent we can measure, they'll be equal. So it is an ergodic state. The state does not remember about initial conditions anymore that deep in time, but fluctuations are very, very large. And it almost looks like it's a more general phase than what we think of as the equilibrium phase. By the way, it doesn't decay for very, very long times. It does decay eventually to precise equilibrium phase, which is amazing. So the system has an initial phase, has this quasi-equilibrium phase, and if it is allowed to evolve, the equilibrium phase. But that comes very, very late in time. So now you know why in the Fermi-Pastor-Ulam-Singo problem, it took 30 years of work and simulations to get to that Proceedings of National Academy of Science paper where this Onorato et al. Showed that that system does go to equilibrium. But they didn't see it because they would often get stuck in this phase. And it is in a phase like this, it's very hard to tell if there is a cutoff or not. And that's the reason why the Livy et al. Study could not conclusively find equilibrium for low energies. Let me stop here. It's been a long class already. So I'm going to wrap this up and make a few comments about the nonlinear Schrodinger equation, and we'll end the class in that note. So which day should we have the kind of oral conversation piece? Should we do it over the weekend, maybe next weekend, or should we do it a little later? We can do it in a weekday also. I mean, it doesn't have to be a weekend. Okay.
Week is fine. Weekend. Yeah.
Which week you said?
Really next week or next weekend. That's all fine.
Yeah, next weekend will be good.
Okay. In next weekend boils down to May 2 and May 3.
Oh, that's this weekend. I was thinking you meant 9 and 10.
May 9 and 10.
Yeah, May
All
9
right.
and 10.
May 9 is good.
Okay.
Yeah.
May 10 is Mother's Day, so I think some of you may be busier
Sure.
than others. So let's try May 9.
And to what extent is this? Is it kind of just like the final from last semester?
Sort of.
Okay.
Vivek hasn't been with us last semester, so it's basically a conversation about all the things we have covered, where I ask random questions and see how people are understanding the material. The project. So how are we doing on the project?
I got it all into an overlay file, so now it's just going to kind of be trimming fat and making it more of, because it's like 25 pages. It's really bloated because it's just like all my thoughts.
Okay.
So if I trim the fat, I could get it down to like 10 to 15 pages probably.
Yeah, as long as exciting results, that'll be fun.
I've
You
taken
said you had exciting results.
Yeah, a small step further with some noise on R. I'd like to take it even a little further, but I've been really busy wrapping up all the graduation stuff. But hopefully I can take it a little bit further and maybe try one new thing, but I'm at least a little further and done something new.
By the way, did you look into the graduation date and reimbursement problem?
Yes, I did. I talked to Dr. Fazzo, and he said that I probably just shouldn't go if I'm not a student anymore. So I rescinded my abstract and requested a refund.
Okay. Yeah, because what happens is that you also may not have your student number active, so that also causes a problem. Okay, that solves it then. If you don't go, then you are.
Right. Yeah,
anyway,
thank you very much for bringing that up.
Oh, you're very welcome. And Vivek, you are also moving along in your market study, right? You said.
Yeah, I'm doing Fourier transform yet, but I have found that normal Fourier transform is not the way to go. You have to do something called Welch transformation. So it's a method to do a Fourier transformation. We are studying this type of financial time series.
I see.
So I will be learning about that, and then I looked at that paper you said.
I don't remember that.
Yeah, probably about 1 month ago, about me and Mukesh, that they tried to predict cycles in financial markets using Fourier transform.
Yes.
And they concluded that Fourier transform is useless. So
yeah. Okay. All right.
That was
Maybe what we can do then is maybe we can, if May 10th May 9th we do the conversation piece, then I don't know about Tony, but if on May 12th we just do both of you doing little presentations on the work, will that be possible?
Well,
mm,
yeah, I don't see why not.
May 12th is a Tuesday,
Yeah.
so we can, instead of me presenting, you guys can rig up your research in a PowerPoint type thingy, and we can just that way I get to listen to them also from you, which always makes reading about anything easier, right? When you hear from somebody. So let's make that into a plan. We'll meet on May 5th, and we'll meet on May 9th, and we'll meet on May 12th.
You want it to be a
okay.
formal presentation or just we like go through the LaTeX file displayed?
Better to do a formal presentation. You'll also have it with you, but it is easier to follow
Okay.
if you have it's not formal, but just put it in a PowerPoint format. You can
Yeah.
just cut and paste like I do,
Okay.
and then insert a few definitions as we have used it. Most times, for example, I use my old stuff, which of course you guys can't do, but a lot of times, for example, when I'm doing something in which I'm not an expert, for example, nonlinear Schrodinger or Korteweg de Vries, I'm not an expert. I don't have a hell of a lot of insights other than whatever studies we have done. So then I go to some standard textbook, or I go to AI resources, or I go to maybe Wikipedia and some other literature and kind of quickly rig up uh, sort of a core level introduction. That's very easy to do, I find. What is not easy to do is for me to show every step in the derivation, because then I have to actually do every step in the derivation before I present. And that takes a bit more time. So a lot of times I do that nowadays, which we couldn't do before, right? In the old days, you had to do all the lit and everything yourself before you could present something, even if it's at a basic level. But nowadays, I find it very, very convenient to do. I won't say it's easy to do because you still should know the material. You still should verify. You can't trust AI. So you take the AI and go through it step by step and make sure there is no mistake. You make sure that it is using proper references. You challenge it a little bit. So you have to do all this stress testing. It's not trivial, but it's still easier to do. And we were having a discussion in the department. We are still going through it as to how students should use AI. And a fundamental problem is how do we use AI? And the point is that using AI is fine as long as you know how to use AI, because whatever you want to get out of it, you'll pretty much get out of it. You have to know that what you get out of it is correct, and you can stand behind it. That's the difference that one needs to go through. Anyway, let's finish here. It's been a long class. All right, guys.
Thank you.
Take care. Bye-bye.